Okay, so let's try again. Yeah, my soul. Here we are trying again, guys. We are trying again. We are doing grade 11 functions. I was here just a few minutes ago, trying to get this lesson up and rolling, and I'm telling you, like, it's like all forces, they came together and they were fighting everything. So alright, so I guess Vodacom is sabotaging everyone. Okay, so hello guys, hello everyone. Just again, earlier on when I started, I was starting with functions, and the whole session on functions basically is we're looking at quadratic functions today. And we looked at the general form of the function for a quadratic in grade 10. This was the general form, ax²+q. So this is the general form of a quadratic function. Then in grade 10, you'll remember as well that this form, your a value gave you the shape of the function. So when a is greater than 0, we know that the function is concave up. All right, smiley face, positive, because greater than 0 means positive. When a is less than 0, we know that the function is concave down, meaning it's sad face, concave down. And then the q value, which is this here, this parameter of q, that informs us about the y-intercept. It also informs us about the turning point, okay? And in order to find, obviously, the y-intercept for any function, we know that we let x be equal to 0. But this y-intercept and the turning point speaks to this q value here, okay? Height value. And then also, what effect does our q have on the function? Whenever the q value is greater than 0, we know that speaks to the function having moved up or shifted up by a certain number of units. Okay, so it's vertical movement. It has to do with vertical movement. When q is less than 0, that speaks to when the function shifts down by a certain number of units. Okay, so we talk about a vertical movement downward. Okay, and then it's very important to know these parameters. The a, like I said, a speaks to the shape of the function. All right, a greater than 0, concave down, concave up, meaning it's smiley face. A less than 0, concave down. And then our q value here, the constant value q, speaks to the y-intercept in grade 10, and also as well as the turning point. So the q value means speaks for two things in our grade 10 function. Then also the effect of q on the function is that the change in q value, if it is a positive value, that speaks to the movement of the function up. Okay, and the more we add to that q value, it means we move further and further up with our function. The entire function moves up when q is less than 0, and in fact when we subtract more and more from that q value, we shift down, we shift further and further down in our function. So let's look at a quick sketch, because in grade 10 we learned how to sketch a quadratic function. So here's the function y is equal to x² minus 4. So first and foremost, we look at the parameters that we have. In other words, what is the a value for x²? Obviously, the coefficient of x² is 1, all right, meaning a is equal to 1. That means a is positive, and if it's positive, it means the shape of the function, we can expect a concave up function like this. That's what we're expecting as far as the shape is concerned, because a is equal to 1, meaning it's greater than 0, so it's definitely concave up. So whenever we are able to establish the shape, we then move on and we use what we call the dual intercept method. We find the y-intercept first. We let x be equal to 0. We take that 0, we go and substitute it into our function. So in the place of x, we are going to substitute 0 in the place of x. So that means we write our function y is equal to, in the place of x we substitute 0, so that is 0 squared in the place of x minus the 4 there. Then 0 squared is 0, 0 minus 4 is -4. That means our y value for our y-intercept is -4. But we let x be equal to 0, so for our coordinates we write the x coordinate as 0 because we let x be equal to 0, and then the outcome after substituting 0 in the function, we get y, which is equal to -4. Okay, so those are our coordinates, and that's very important. Okay, these are our coordinates for the y-intercept. It is also our turning point, because remember we established that the y-intercept is also the turning point for our grade 10 quadratic function. Okay, then after that we use y is equal to 0. We let y be equal to 0 to find what we refer to as the x-intercept for the very same function. So if we let y be equal to 0, it means we are going to have 0 is equal to x squared minus 4. We then factorize this expression, x squared minus 4, to get x plus 2 into x minus 2 as per our grade 9 factorization and grade 10 factorization. Then after that we get x is equal to -2 or x is equal to +2. These are our x-intercepts. In other words, this is where the graph cuts the x-axis. So when y is 0, x is -2. When y is 0, x is +2. So these are our pair of coordinates. If we go now and draw on the graph, we draw our y-axis, we draw our x-axis, and then all we do is we mark our y-intercept as 0 and -4. So that means the -4 for y, which is basically down here, that's where the y-intercept is. And then the -2 for x, the +2 for x, that means -2 for x is here, and then the +2 for x is right there. So we mark the x-intercept +2 and -2, and that's where the graph cuts through the x-intercept, turns at the y-intercept, as well as it turns here, because the y-intercept is also the turning point. Then it goes around, cuts the x-intercept, and continues on in that direction until infinity in our direction to the right for x. So basically this graph is an unrestricted parabola graph that is concave up. In other words, it is a smiley face graph, and basically it is the way that you see it. So we get a mark allocation for actually making sure that we sketch the graph with the right shape, because this is a nice smooth curve passing through the turning point into the x-intercept. So this is a beautiful curve, right? And also our x-intercepts are marked and labeled. So basically we get marks for the x-intercept, we get a mark for the y-intercept being marked, and then we make sure as well that our shape, please guys, all right, it must be a parabola that truly curves or turns at the turning point and increases. So the graph here, what happens as we move from left to right is that the graph is decreasing, goes down, because if you think about y, if the graph is going in this direction, the y values are going down. So it's a decreasing graph from here all the way. It goes to the turning point, continues to decrease, and at this point it turns, right? And then it increases, right? Because we're now going up. Do you see that? So we decrease, turn, increase, right? That's very important. So then we look at something that we refer to as the domain. What is domain? When we speak about domain, we speak about the possible x values where our function exists. The possible x values where our function, meaning our parabola function, where does the function exist? And when we say the possible x values, remember our x values, we are referring to the values from left to right. So we are asking ourselves, where does the function exist? For which x values does the function exist from left to right? So you can see that this function, like I said, is coming all the way, turns, continues all the way, and it infinitely does so. These arrows there at the end show you that this function is actually just continuing, like it's infinitely coming down from this side, infinitely going up from this side. And basically what happens, it does that from left to right infinitely. It's unrestricted, which is why when you speak about the domain of this function, we say that x is an element of all real numbers. All right. In other words, we're saying that this function exists for every x value from left to right. This function exists everywhere from left to right. That's what we mean by x is an element of real numbers. Or some people tend to say x is an element of, open brackets, from negative infinity. So the symbol here is negative infinity. It's like a 8 that is lying horizontal from negative infinity to positive infinity. So x is an element of negative infinity to positive infinity. That just shows that the function exists everywhere from left to right. Okay. So remember, when they ask domain, they are simply asking where does the function exist from left to right. Okay, remember this will be posted up, so you guys, if you missed anything, you'll be able to backtrack on it in the YouTube channel and check out what it is I started off with. So this is just a recap on grade 10. I really am just going through this fast so that I can be able to get onto the grade 11 content for parabola. Range. What is range? Range is the possible y values where the function exists. Okay, the possible y values where the function exists from bottom to the top. Okay, so if you look at this function, where does it exist from bottom to the top? So this is like you having this horizontal line. This is where the function exists from the bottom. Okay, it doesn't exist below this -4. But it does exist at -4, and it exists everywhere above -4, and infinitely so. So it goes on. So at -4, it's there. As we continue above -4, it's there, it's there, it's there. And these arrows, because they infinitely go, it means that the function will exist infinitely above -4. So that's why we say, when you write the range, from the bottom to the top, the function exists y. In other words, y, because remember, when we're speaking about range, we are speaking about the possible y values. We'd never say x is greater than, no, because we are talking about the possible what? Y values, where the function does what? Exists. From where? From the bottom, because these are the smallest y values at the bottom, to the top. So we say y is greater than -4. Of course, it has to be greater than. In other words, it has to be above -4. But also it's equal, because the function does actually touch or does exist at some point here at -4. So therefore, it's very important to say y is greater than or equal to -4. Someone else writing the same range would say in interval notation, because there's another way of saying the same thing just in a different way. All right, y is an element of square brackets -4 to infinity, open brackets. So this is the same answer as this one, just that it is stated a bit differently. In other words, y, okay, is an element starting at -4. Well, now these brackets, these square brackets, means that -4 is included as part of the range all the way. This here means 2. So it's -4 to infinity. Now, infinity is just simply a concept in mathematics that shows that it goes on endlessly with no end, forever and ever and ever. You know, it's like most young men in their youth, you know, when they supposedly, you know, young people, I've seen this like even in schools respectively, you'll find that young boys and girls will supposedly, you know, claim to be in love or, you know, be in a relationship, and then this boy will sort of like profess their undying love to this person that they will only know for probably a few months or maybe even a few years, and then after that, like, they'll just forget about that particular person and they'll declare their love and they'll be like, I love you and I will love you forever. And you ask yourself the question, is it even going to be feasible? So it's not that kind of infinite love that we're talking about here, or that no end, because here literally means no end, like forever and ever. It will continue, this graph will continue above this -4 infinitely, you know, with no end. So there's a profession of really truly undying, ongoing, perpetual existence for the graph above -4. Unlike the profession of a young man who is obviously knows nothing about this concept of love. Anyways, that's just an example to emphasize my point. Doesn't mean anything really. So y is equal to -2x² plus 18. Let's look at this one, guys. Y is equal to -2x plus 8, -2x² plus 18. What's different about this graph is that unlike this one, this function, the coefficient of x² is not positive, but it is actually negative. So we have y is equal to -2x² plus 18. So a here, the coefficient of x² is -2, which means a is less than 0. So what are we expecting from the graph? Boo, very sad. No? Yeah, sad face. In other ways, concave down. I mean, when someone is negative, you know most they are down. So it's concave down here. All right. So this will help us in knowing the shape, of course. Then we need to find the y-intercept. When we find the y-intercept, what do we do, guys? We let x be equal to 0. Substitute 0 in the place of x. Y is equal to, in the place of x, we substitute 0. -2 into 0, the whole thing squared, plus 18. We then solve. We get y is equal to positive 18. Then we write our coordinates. So that means y-intercept. This is where the graph cuts the y-axis. We have 0 and 18. Okay. Then we go for our x-intercept. You know, our x-intercept usually for our parabola function, we tend to have 2 x-intercepts, right? Because quadratic x² implies that, you know, ideally we should have 2 roots, but that's not always the case, guys. So here, -2x² plus 18. When we solve for x, we divide by -2 because it's the coefficient of x². This ensures that we are able to make sure that we get x² minus 18, because a positive divided by a negative here will give us a negative, and 18 divided by 2 is 9. -2 times divided by -2 gives us 1, which is positive 1x². Then we can factorize. It's a difference of 2 squares. We get x plus 3 into x minus 3. We get those x coordinates, which are also our x-intercept. Remember, we let y be equal to 0. So it stands to perfect reason that our coordinates, when we write them, is -3 for x and y is 0. We get a positive 3 for x and y is 0. These are our x-intercepts. We go and mark them on our Cartesian plane. -3 and 0 is there. That's -3. Positive 3 and 0, remember that's on the x-axis, so that's 3 and 0 there at that point. And then our y-intercept, or turning point, because it's also the turning point, is 18. And then we sketch the graph, and obviously the shape should resonate with what we had expected, because we're expecting a sad face. There it is. We began our function with the end in mind, that we would come up at the end with a concave down function. And that's exactly what we were able to discover when we sketched the function. Thank you, BE. I really appreciate the ice cream. So thank you, guys. That's basically how we did things in grade what? In grade 10. The functions that we did back then in the days, right? And those are fun times, weren't they? Very, very fun times. Very, very fun times, all right? Okay. Now we are going to move on slightly and enter into the grade 11 zone, all right? Because by doing that, I was simply recapping and just wanting to remind us what the condition or the state of our function was like when we did grade 10, so that people can have a very, just sort of like be reminded of that. There was a reason why we did that in grade 10, because we saw that there were limitations with the function in grade 10. Our function in grade 10 simply moved up and down. That's all it ever did. It moved up and down. It would compress and it would stretch. All right. So it would compress and stretch, move up and down, compress and stretch, move up and down. That's all it ever did. So boring. All right. But now all of a sudden, when we come to grade 11, there are two important forms of the quadratic or parabola function that we get in grade 11. The first form is y is equal to ax² plus bx plus c. Now you're not seeing this form for the first time. When you guys did how to complete the square of a quadratic expression, you were in essence exposed to the quadratic form of the parabola earlier on in the year when you did term 1. All right. And I even in the platform did it for those who actually started off early with me when we did the quadratic expression and how to complete the square of that quadratic expression, therefore finding the minimum and the maximum value, and the value of x that gave us the minimum and the maximum. We did actually get exposed to this form. This is what we refer to as the quadratic form. Okay. All right. So please, guys, let's be here together with this because it's very important. All right. Now, I want to unpack what these parameters, guys, we call A, B, and C, we call them parameters. Okay, because they have they sort of like give us an idea as to how we can expect, okay, our functions to be like. All right. Yeah. So A, I think we've already exhausted A. If you didn't get it the first time round, A can either be positive or negative. This is what we expect when A is positive. We're expecting happy people. I don't know, parents, they usually say parents are happy people. But we're expecting happy people, you know, not sadness, because A is greater than 0, it's positive. Okay. Then here, A less than 0, we're expecting what? We're expecting this to be concave down. Sad people. Okay? That we know. That we know. Now let's look at B. All right. Let us look at B. But first and foremost, before we look at B, I want us to see something here. This C here has to do with the y-intercept. It has to do with the y-intercept alone. Remember, if you let x be equal to 0, all right, the minute you let x be equal to 0, boom, boom, this goes, because this all becomes 0, that goes, this all becomes 0, and then you get left with the y value, all right, the y-intercept in other words. Okay, yeah. So this basically helps us to know where can we expect will the function cut the y-axis? Will it be cutting it above the x-axis, or will it be cutting it below the x-axis? And that's very important. Where are we cutting? Where is the function? Where is function cutting y-axis? All right. Okay, I hope you are with me there. The b value. so obviously, guys, if c is greater than 0, you know most, then we are cutting. Where are we cutting? Where is the function cutting the y-axis? It's gonna cut it above the x-axis. Okay, cut above x-axis. The minute c is less than 0, then obviously it's going to cut below the x-axis. All right, so hopefully you understand that. Okay, b has an effect on the turning point. B affects the turning point, but I want for a moment, just for a moment, guys, to just explore a few avenues here. There's something I want us to explore together, right, so that we can sort of like also have a bigger you know, sort of like understanding as to like this b value, what it does and all of that stuff. Okay, because b and c kind of worked together. B and c, they work together. Okay, they work together, and remember, in our function for grade 11, there's a movement of the graph left and right. Okay, remember, in our function in grade 10, there was no movement left and right. All right, so the turning point here changes for our quadratic function in grade 11, and this b value has to do with that as well. All right, but I want us to explore a few things here. Let's just say we were given a function x squared, let's say plus 2x plus let's say x squared plus 4x plus 3. Okay, x squared plus 4x plus 3. This means a is greater than 0, b is greater than 0, c is greater than 0. The thing is, nowadays, guys, this is the interesting thing. Nowadays, they usually ask us to draw rough sketches of your quadratic function, and all they usually do is they will probably like just give you these. They'll say, draw a rough sketch. Draw a rough sketch of a parabola, because nowadays, right, you know, they don't need numerical values to basically ask us to sketch a function. Sometimes they will just use the parameters, and they will give you those, and they'll say draw a rough sketch of the function using the parameters. So what I want to do is I want us to really truly understand what do these a and this b and this c, what effect do they have on the function. Okay, and I want us to sort of like see this and see it very well. So if you look at x squared plus 4x plus 3, for instance, right, a is positive, b is positive, c is also positive. So all three of these are positive. These parameters, they are all positive. So if we look at them respectively, you remember, you know, most when we let x be equal to 0, we are trying to figure out sort of like where can we expect or anticipate will this function, where will it exist? So we know, obviously, since a is positive, we know that the function will be concave up. So our shape, we know, is going to be like that, no problem. Our c value, it's clear, most, that our c value, we are going to find the function. It's going to be located, the y-intercept will be cutting through the y-axis above the x-axis. We have no problem about that. Okay, then of course we have this beautiful coefficient of x, okay, and that is 4. So if you were to then factorize this, because I usually say most, we know that when the coefficient, when the constant is positive, then we know that it means that we have the same signs inside the bracket, and it will always be according to the sign of the middle term. So that means we're going to have plus plus. Okay, I hope you understand that. Okay, in Xhosa we usually say siyafana. Plus means siyafana, meaning we are the same. And then we ask sifana nabani, meaning who are we the same as? And we say nalo, meaning this one. And then we say sobabini. So sifana nabani, nalo, sobabini. So basically there are positive signs inside the bracket for both. And then obviously what does that mean? It means we are going to get roots that are negative. So 3, 1, x and x. Obviously that means x is equal to -1 or x is equal to -3. Guys, can you see that essentially these roots are going to be located on the negative side? The negative side of our x values. This function is not going to exist to this side, the positive side. It's going to exist on the negative side of our x values. Okay, remember the 0 here. The x values that are positive are on this side. The x values that are negative are on this side. So this function in particular will exist on the negative side of our Cartesian plane. I hope you guys understand that. So in essence, if you are given a sketch, if you are given the parameters of A, B, and C, and all of them are positive, roughly speaking, if you are going to draw this sketch, you know that A means we have a concave up graph, no problem. C, since it's positive, means that there's going to be a y-intercept that is going to be above the x-axis. But then this B, the relationship between B and C, since C is positive and B is also positive, that therefore means that our x-intercepts are negative. So roughly speaking, this would be a appropriate sketch to then sketch if you are given these parameters. Okay, so that's why I'm saying, guys, that understanding these parameters is of extreme importance. All right, I also want to state that your turning point here, all right, you want to establish in your head your turning point. Okay, now in grade 11, guys, when we are having our quadratic expression or the quadratic form of the function as ax²+bx+c, we actually have a formula that we use to find the x coordinate of the turning point. So in this case, x is equal to -b/2a is the formula that we use to find the x value of the turning point. Very important. All right, and you will see this x is equal to -b/2a when you are in the process of completing the square of this expression, which you have done. You will see this x is equal to -b/2a in that process when you are completing the square of this expression, which is something we did in term 1. So this x is equal to -b/2a is founded on that. It's coming from that. It has its origins and its foundations from that idea, because to get the x coordinate, the x value, which will give you either the minimum or the maximum, this is your expression that you can use to find the x value that will give you a minimum or a maximum in a particular quadratic expression. So x is equal to -b/2a is what we use. Now think of this. So b is going to be some positive value. So that means this negative is there. There's a b. So in this case, you can see we have 4. That is positive, of course. Okay, so it doesn't change the negative. 2, the a is also positive. The outcome you are going to get from this is a negative value. Okay, obviously we can find a specific value, which is -2. This is the x coordinate of the turning point. We don't have the y value or the y coordinate of the turning point. So what we usually do to find the y value is we substitute the x value, which is -2, into the original function. Into the original function. So if you see the turning point, the b plays a prominent role in affecting the turning point. Hence, we are saying that b will affect the turning point because in this situation, because the function is expressed in this form, it also speaks to the movement or the horizontal movement of the graph, left and right. So our turning point is no longer the y-intercept. Our turning point is different from the y-intercept in grade 11. And this is very important. Our y-intercept in grade 11, the function, is different from the turning point. And this is very key. Very key. They are no longer the same thing. You know, in our grade 10 function, we spoke about the y-intercept and turning point interchangeably because our form, this form, spoke to the fact that there is no middle term. There is no middle term with what? With the x variable. Okay? There was no middle term with the x variable here. There was only the x squared term, which had the coefficient which spoke to the shape, and there was also the constant term. There was the middle term had 0. You know, we could write 0x, right? At the end of the day. At the end of the day, it's ax²+q. It's not that the coefficient for b is not there. For x is not there. It's there. It's 0. But at the end of the day, that means no effect. All right. But now all of a sudden, we can see that for this one, the turning point and the y-intercept were 1. Here, it's not the case, guys. It's not the case at all. The y-intercept is different from the turning point. Okay, so if we take now this x value of the turning point, which we got by using the formula x is equal to minus b over 2a, and this is a very important formula that you need to know for now and forevermore. You take that x value that you got, you substitute it into the original function. So we then go say y is equal to, there's the original function, x² plus 4x plus 3. Let's substitute the negative 2 in the place of x. Negative 2 squared 4 into negative 2 plus 3. And then we can do the formulation. The square, the even exponent to the negative side makes it positive, so it's positive 4. And negative 8 plus 3, that's 4 minus 8 plus 3, and of course that's negative 4 plus 3, which is negative 1. Okay, so therefore our turning point is negative 2 and negative 1. Okay, all right, very, very important. Okay, so remember here we got the x-intercept. Here we let y be equal to 0, and that's why we're able to get x is equal to negative 1 or x is equal to 3. And when we write it in coordinate form, of course, that's 3 and 0, negative 1 and 0. Our shape, we know because a is equal to 1, it's positive. That means we have a concave up function. 3, now we can get our turning point using this formula. X is equal to minus b over 2a. b is the coefficient of x. There it is. We write the negative, obviously, as the formula states. Then in brackets, we put the 4 over 2. The 2, we substitute in the place of a the coefficient of x squared, which is 1. So it's 2 times 1. We get negative 4 over 2. The division of these two gives us negative 2. That is the x value of the turning point. To then get the y value, we substitute the x is equal to -2 into the original function. We get y is equal to, in the place of x, we substitute -2 all the way through, and then we get y is equal to -1. So that means our turning point is -2 and -1. The last thing we need is the y-intercept. So for that very same function, we're going to let x be equal to 0. We take that function y is equal to x² plus 4x plus 3, 0, 0. Y is equal to 3. Coordinates 0 and 3. I'm sure you can see the turning point is -2 and -1, whereas the y-intercept is 0 and 3. They are not the same thing. Okay, so now we are in the position to sketch. Very beautiful position to sketch our function. All right, please people, thank you Mbali, please people, it's very important. Beautiful position to sketch now. Okay, all right, just a recap again. This was our function. From the function we saw that a is positive, so we expected the shape of the function to be concave up, no problem. We then found our x-intercept, grade 11. We let y be equal to 0. We factorized this. We got x plus 3 into x plus 1. We got x is equal to -3, or x is equal to 3, -3, sorry. Not -3, both -3 and -1 and -3, because x plus 3 and x plus 1, we get x is equal to -1 or x is equal to -3. Then of course our coordinates, if we were to write them, it's -1 and 0. We have -3 and 0. Where does this 0 come from? We let y be equal to 0. Remember, these values of x belong here in the first position of each coordinate point. What follows is what we let y be 0. So in the place of y, we write 0 for both the x-intercepts. Very important. That is how we found our x-intercept. After that, we went ahead and found our turning point. How? We have a formula that we use to find the turning point. It's called x is equal to -b over 2a. That's how we get the x value of the turning point. If our function is in this quadratic form, that's how we find the turning point. So we got x is equal to -b over 2a. We substitute in the place of b. The b is the coefficient of x, which is +4. There it is, we substituted it in brackets, over 2 times a, which is 1, the coefficient of x squared, 2 times 1. Then it's minus times 4, which is -4, over 2. Negative divided by positive gives us negative, and 4 divided by 2 gives us -2. After getting that x coordinate of the turning point, we take it, we substitute it back into the original function. Substitute x coordinate into the original function. There's the original function. We take the -2, we substitute in the place of x, where x is, we use brackets, please. We substitute -2 where x is, and then we simplify. And please guys, the simplification should be of no problem, because when this substitution and simplification were things that we did in grade 8 and 9, we've established them well, so we shouldn't be making any silly mistakes with the signs and with the addition and so forth. Your calculator is there, you just substitute everything and you make sure your mode is in the appropriate mode, and then you get the answer. So y is equal to -1. The point x that you got was -2 for your turning point, and the y is -1. What is now missing is the y-intercept, because like I said, the grade 11 theory was that we do not in any way think that the turning point is the y-intercept for this type of function. So we then let x be equal to 0. We substitute, you can see we get a y is equal to 3. That is our coordinate of the y-intercept. They usually sometimes ask, what is the y-intercept? If they ask what is the y-intercept, you can simply say that the y-intercept, y-int is equal to 3. But if they ask you what are the coordinates of the y-intercept, then guys, this is what you need to make sure that you write. These are the coordinates of the y-intercept. And there's a different distinction. There's a distinction between these two questions. If they say what is the y-intercept, you can just write y-intercept is equal to 3. If they ask you what are the coordinates of the y-intercept, then you have to state the coordinates 0 and 3. Very important. As you see it in this brackets, open brackets, 0, and then you write a semicolon, which means and then the 3, you close the bracket. Okay. Now we can go now and sketch. All right, like I said, you just draw your beautiful Cartesian plane. Let me just redraw it. Then your -3, your -1. In between, there was that turning point, which is x is -2. X is -2 is midway between -1 and -3, which makes sense because this here is supposed to be what we call the axis of symmetry, the line that cuts the parabola function into equal halves. Then if the -2 is there, the y for -1 should be here somewhere. Okay, so where these two meet is there, and all that is needed is we need to check the shape. Remember, we said a was positive. What does that mean? It means we're expecting a concave up function. So all we do, we turn. Okay, we turn. But you see, what would have been nice, of course, is that you make sure, I think I made a bit of an error there, because what I want to do is to make sure that the y-intercept is there. All right, so okay, let me just redraw this so that we can make sure, because you see I didn't label everything before I drew. So we have 3 here, -3, we have -1 here, have the +3 possibly there, and then obviously you have the -2 here. That is your axis of symmetry. Very important, that axis of symmetry. -1, that's there, so that's where these two meet here. Then all you do is you connect these guys, you make sure that turns there. Okay, I'm sure you guys can see now. Beautiful shape, that one. I'm sorry about the interference of all of that I did there. I think I squished it up a little bit there. Okay, I think if I had opened it up a bit, like, and more space, maybe I'll just redraw it somewhere else. Let's just do that, so that, yeah, let's just, so this is very much freehand. You can see very free, this hand. So let's just say -1 here, right? And maybe what you see me doing here is that I'm focusing really primarily on just those points that I had. Okay, I'm not really focusing on anything else but just that, because all I want is to just sketch, including the most important things that basically were, you know, referred to in the x-intercept, y-intercept, the turning point, because those are most important. And obviously I need to make sure that that axis of symmetry is also there. Okay, so -1, so that's where we meet. The -2 is here. So what we do is we simply turn there. Okay, let's just bring this 1 a bit closer than -1 here, right? And let's just say that 3 is here. Okay, so that there is a sense of integrity in my drawing. Okay. Okay, I hope you guys get the point. So basically this is a curve. It's nice, small. It passes through the x-intercept, -3, turns at -2, passes through my x-intercept there, passes through the x-intercept. It's just, I simply slightly moved it to 3 there, so that make sure that it's reflecting all the important points. Okay, then I also make sure that I write the equation x is equal to -2, because this is my axis of symmetry, right? Okay, so that x-intercept, that's -3, and then obviously let's mark the turning point there, which is -2 and -1. We have -1, the x-intercept, and then we have +3 here, the y-intercept as well. And then we label the graph y is equal to x² plus 4x plus 3. Okay. And then who can say we don't get the marks that we're supposed to get? Okay, guys, this is the one place where you can actually use a pencil to sketch. Okay, so that at the end of the day your diagram is not as untidy as you see mine being, because I've used pen and I made errors there and there. So the errors that you make, you can rub off and you can sort of like redraw. Okay, what's important there is just for these things to appear. Your x-intercept, they want to see that you can see, oh, the -3 is there. Your x-intercept, -1. Your axis of symmetry, I would insist that you make sure that you draw that in, you label it, and then you label your turning point, okay? The coordinates of your turning point. And then your y-intercept as well needs to be very clear. That 3 must be clear there, okay? So that is how we sketch our parabola function, guys. This is for grade 11 and grade 12. Because this concept of drawing your sketch can definitely be examined, all right, at grade 11 and grade 12 level. Okay, yeah, very much so. So yeah, I don't know if there's any particular questions that people have right now. As you are looking at this, you maybe have any question maybe ringing in your head right now about anything that we've spoken about. So that's A, B, and C. Okay, then there's another form for your parabola that your parabola can appear in grade 11. The y is equal to a into x plus minus p, the whole thing squared, plus minus q. Okay, your parabola can also be expressed in this form. We call this the turning point form, right? You saw this form when you completed the square of an expression and you were able to read certain information from the sketch utilizing that form. All right, you were able to find your minimum value or your maximum value, and you knew that what dictated the minimum and the maximum value was your value of a. If a was positive, that meant smiley face, concave up, it meant you had a minimum. If a was less than 0, it meant concave down, and it meant you had a maximum. Okay, I'm sure you guys remember that. Very, very important, remembering that thing. Okay, so yeah, the turning point form is also very important. The turning point form. Okay, it's just that right now I'm trying to be. So let's look at one particular turning point form that maybe we can see how would we sketch this turning point form. Let's say y is equal to 2 into x plus 1. Okay, so if we had this function and then we were asked sketch this function, okay, maybe some of you are looking at this and you're like, how would we go about sketching this function? So let's change the plus to minus, just for fair game. Okay, so a few things. We always seem to start here. Okay, our a value, a. So a still speaks to shape. A greater than 0, a less than 0. So nothing has changed there. Okay, then here the P, the inverse of P is the x coordinate of the turning point. What are you saying here, sir? The inverse of P is the x coordinate of the turning point? Hypo. Really? Yes, indeed. Okay, what about Q then, sir? Q as it is the y coordinate of the turning point. Okay, so sir, what are you saying? I'm saying A obviously speaks to the shape, nothing has changed. P, the inverse of P, all right, is the x coordinate of the turning point. Q as it is the y coordinate of the turning point. Now furthermore, I want to say P speaks to horizontal shift. Okay, P speaks to the horizontal shift of the function. Okay, so if P, all right, in other words, is greater than 0, we say that the graph moves to the left. But if P is less than 0, we say the graph moves to the right. Okay, there is this sort of like counterintuitive nature that the p-value has. You know, so for instance, what you would think normally is that if you are saying p greater than 0, that means positive. And if you're looking at your x-axis, you're like, in your head, it should be moving to the right, shouldn't it be? And that's what you think, right? But then it's actually not what you think. It's counterintuitive. In other words, it's against normal thought. It is the opposite of what you think. So when p is greater than 0, that speaks to movement of the graph to the left, in actual fact. Okay, so that's p. And this counterintuitive nature of p is applicable not only to the parabola graph, it's applicable to the hyperbola graph, it's applicable to the exponential graph. So it's also applicable to the exponential and the hyperbola graph, as well as the quadratic or parabola function. Okay, so this is always the case for your exponential, hyperbola, parabola. When p is greater than 0, we talk about movement to the left. When p is less than 0, we're talking about movement to the right. Okay, then as for q, nothing changes. Q greater than 0, we're saying up. If q less than 0, it's down. Okay, nothing has changed with the q value. It's up, down. The same up, down that was there in grade 10 is the same up, down we have in grade 11. It's the same up, down we have in grade 12. So in other words, the isolated constant value, because remember, sometimes the letters, they will use different letters. Maybe they may use different letters. So it's just important here to note that the constant value that is isolated from the binomial square term is that value which speaks to the y coordinate of the turning point, and it also speaks to the movement, the vertical movement of the graph. When that value is positive, we are talking about a shift up, but when that value is negative, it's a shift to the down. Okay, but this one p, counterintuitive, né? Let's not forget that. Okay, I don't know if there's any questions, please do ask. So if we are sketching, okay, we're always starting with a is equal to 2, it's greater than 0. What we're expecting concave up. Already we know our shape. We are beginning with the end in mind. We know what we are expected, the outcome. Okay, that's a. Then we move here. We have x plus 1, the whole thing squared. Remember, the next thing we want to look at is turning point, because we know that speaks to turning point. X plus 1, we said the inverse of p is the x coordinate of the turning point. So in this case, the p value is plus 1. So the inverse of p, x is equal to, that means in other words, the inverse of plus 1 is minus 1. So the x coordinate of the turning point is negative 1. The remember this x coordinate of the turning point also speaks to the axis of symmetry. Okay, so that's why this is important. It speaks to the axis of symmetry as well. Okay, x coordinate, remember the x coordinate of the turning point was negative 2, but it also spoke to axis of symmetry. Okay, very important, guys. Thank you, Luanda, for the rows. Really appreciate it. So x is equal to negative 1. That's the x coordinate of the turning point, but it also speaks to axis of symmetry. So here, there's no formula that is needed. For the turning point form, we can simply read the x coordinate of the turning point. But you remember for the quadratic formula, not the quadratic formula, the quadratic function, ax²+bx+c, this form, it requires a formula to be used to get the x coordinate of the turning point. Then we take that x coordinate, we substitute it into the original function. So for this form, there's no need for a formula. All we need to know is how to get the x coordinate of the turning point, and that is, we know it's the inverse of the p value. Okay, some people even take this x plus 1, they will put it in x plus 1, they will equate it to 0, then they will transpose the x and say x is equal to negative 1. They know that this is the axis of symmetry, but it is also the x coordinate of the turning point. You see? Okay, I hope you guys understand this. Now, after the x coordinate of the turning point, which is the x of symmetry, what else do we need? The y coordinate of the turning point. What did we say is the y coordinate of the turning point? We say it's the value, this constant value as it is the y coordinate of the turning point. So what is the q value as it is? It is negative 8. So that means y is equal to negative 8. The turning point. So therefore that means the coordinates of the turning point are negative 1 and negative 8. We are going nicely. We've gotten the shape, we've gotten the turning point, the x coordinate, which is the axis of symmetry as well. So we know the equation of the axis of symmetry for our parabola. We have gotten the coordinates of the turning point, because the inverse of p is the x coordinate of the turning point. The q value as it is the y coordinate of the turning point. So if you go back to those questions where they said, for which value of x do we get a minimum? The value of x would be negative 1. The minimum value would be negative 8. Oh, the x value that gives me a minimum. And it makes sense, negative 1 is a minimum. Okay, this thing. Why? Because negative 1 is my bottom value. Hey, so if I was to write the domain, for instance, of this function is unrestricted from left to right. Yes, Musa, maths is really a game. From left to right, the function is unrestricted from left to right. So if I was writing the domain of this function, I would say x is an element of real numbers. The function exists everywhere from left to right. There are no restriction. There are arrows on either side of the function. What about its range? If I was writing the range of this function, this idea of minimum, the minimum y value is negative 1. The function starts at negative 1 from the bottom. To the top, it goes on infinitely. So that means if I route the range, I would say y is greater than or equal to -1. In other words, y is greater than or equal to that minimum value, which is the y value, which is -1. That makes sense. Okay. Or if you were someone else, you could say y is an element, square brackets, -1 to infinity, open brackets. I mean, this would be the same answer. So this domain and range idea, so guys, straightforward. There's no problem there. Okay, so let's go back to the sketching. A, tick. A is equal to 2, A is greater than 0, smiley face. 2, my turning point, where the graph will turn. All right, the axis of symmetry, the x-coordinate of the turning point, I know will be the inverse of the p-value. So the inverse of +1 is -1. That's the x-coordinate of the turning point. My y-coordinate of the turning point is q as it is. As I see q, that is my y-coordinate of the turning point. So there are my coordinates. Let's move on. What's the next thing in line? Y-intercept. For y-intercept, I let x be equal to 0. So I'm going to go to that function. Let x is equal to 0, 2 into 0 plus 1, the whole thing squared, minus 8. 2, obviously, 0 plus 1 is 1 squared. And then 2 minus 8 is -6. So y is equal to -6. So if I was writing the coordinates of the y-intercept, I would say x, 0, and -6. Okay. Slibo wants me to explain the domain and the range again. Okay. Slibo, domain is simply the possible x values where your function can be seen or where it exists. Okay, and you usually look at the domain from left, when you read it from left to right on your Cartesian plane. So this is the function, this is the function. You can see this, it decreases, 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 turns, increases, increases. These arrows show that infinitely, so it's decreasing infinitely. In this side of the axis of symmetry, there's infinite decreasing. All right, infinite decreasing from left to right. All right, there's infinite decreasing. Cat Chris, we are doing functions in grade 11 and grade 12. Grade 11 and 12 functions, and we are doing the parabola or the quadratic function at the moment, and we're just looking at how to read or identify the domain, which is basically how to get the possible x values where the function for our parabola exists. So from left to right, like I said, Slavo, we are decreasing infinitely here. Then what happens here? We turn. That's nice, Cat Chris. Then we turn here and we increase. Okay, so this function, it means that it will forever exist from left to right. As the arrow is there, it means that the function is unrestricted. So if you are moving along this horizontal x-axis, if I'm coming from this side, from -infinity, the question is the function there? Yes, guys, look, it's just that there's no space for me to draw. This arrow means that it continues forever and ever without any end. So from -infinity, the function is there. It's there, it's there, it's there, and it's above the x-axis all the way from -infinity. The function is there above the x-axis. And then at -3, it's on the x-axis. The minute I surpass -3, this function is still there, but it's below the x-axis. It's below the x-axis. It's below the x-axis. Then at -1, it's on the x-axis. I continue from -1. Hey, it's above the x-axis. It's above, but it's increasing at a very, very, very increasing rate. So you can, the function, if this arm was allowed, the arrow is just to denote that this goes on, guys. it goes on. So the function seems to exist for every x value. From left to right, the function exists everywhere. There is no x value where you can say, in this x value, the function is not there. For every x value from left to right, the function exists. So that's what our domain is. It is the x values where the function exists. And when we look at x values, we are always looking from left, because from left is our most negative values, to the right to our most positive x values. So the function exists everywhere for our x values. I hope that's clear for you, Libo, for our domain. Then when we look at range, we are looking at the possible, not x values this time, but we are looking at the y values. So that's why when you write your answer, there needs to be y. You can't be writing domain and then you can see x in there. No. Domain means possible x values where the function exists, and we are looking from left to right when we look at the domain. For our range, we are looking at the possible y values. Possible y values where the function exists. All right. Okay. Jose, can you show for which graphs you say x is an element of R? This one. So the parabola exists everywhere. As long as there's an arrow on each end, it means that the function is not restricted. There's no restrictions to the function. Okay. Remember, x is an element of R means that for all real values, the R means real values. What are real values? Real values are all rational and irrational numbers. On this number line, we are not only accounting for -3, -2, -1. No, we are accounting for every single number in between -3 and -2. That means all rational and irrational numbers on the x values. All rational and irrational numbers. Hence, we say that the function exists every single value of x that you can imagine. The function does seem to be there for every x value. For instance, if I take an x value here and I substitute it into the function, there is some output that I will get. If I take any x value, let's say -1 million, and I substitute it into the function, there will be some output value that I will get, which means the function does exist in those x values. So for every single x value that you can imagine, the function does exist. That is for a parabola that is unrestricted. And I repeat, guys, if the parabola is unrestricted, in other words, there's no beginning, there's no end from left to right. That's why I'm saying these arrows denote there's no beginning from the left, there is no end on the right. There's an infinite continuation of the function from left to right. Okay, so that's very important. So that speaks to domain for our parabola. Then range is the possible y values where the function exists, but we don't look from left to right, we look from the bottom to the top. So this is like started from the bottom, now we're here, you know. So started from which bottom? This is the bottom of the function. Remember, when a is positive, it's concave up, smiley face, there's a minimum. Minimum means the bottom part. Which is the bottom part or the minimum? Our minimum value is -1 here. So when you write the range, it means y is equal to -1, but it's also greater than -1, meaning the function is found above. Greater than means above the y value that's -1. So it's on -1, but it's also above -1. You can see, guys, when I move above, you can see the function is still there. Look at that, you see? But if I look below this line, there's no function that you can actually touch below the line -1. But at -1, it's there. just 1 point touches. Above -1, it's there everywhere. Okay, so that's why we say y is greater than or equal to -1. Okay, so you're always checking what are the y values where the function exists. Okay, all right guys, I hope Libo is sorted now with the explanation of domain and range. You see now, where was I? We had spoken about getting the value of a so that we can know the shape, getting the turning point from this form. Remember I said the inverse of p is the x coordinate of the turning point. So +1, -1, the inverse of +1 is -1. That's the x coordinate of the turning point, which is also the axis of symmetry. Y coordinate of the turning point is this constant value that is a standalone. As it is, it's -8, so therefore it becomes the y coordinate of the turning point, which is -8. Then I said to you 3, we need to find the y-intercept. When we find the y-intercept, we let x be equal to 0. We substituted, we got y is equal to -6. Remember, what did we let x be? 0. Y is -6. Those are the coordinates of the y-intercept. 4, we need the x-intercept. We let what? Y be equal to 0. So we go and write that function. We equate it to 0. Remember, it was y is equal to, but it doesn't matter whether you write that y this side or not. This helps with convention, so I can solve. So 2 into, if x plus 1 is there with the whole thing squared, okay, x plus 1 the whole thing squared, then it means x squared plus 2x plus 1 minus 8 is equal to 0. Then I can solve by distributing the 2 to the x squared, to the 2x, and to the 1. Okay, so I get 2x squared, 2 times x squared is 2x squared, 2 times 2x is 4x, 2 times 1 is positive 2, then that minus 8 was a constant term. So then obviously now I have like terms that I can add. I have 2x squared plus 4x. 2 minus 8 is -6, which is equal to 0. I'm sure you can see that there's a constant highest common factor, which is 2. So I can divide by that coefficient. So I can get x squared plus 2x minus 3 is equal to 0. And then I can factorize. Okay. When we factorize this, factors of 3, okay, remember negative says we are not the same, but the factor that has the highest will have a positive sign. So I have x, highest factor will have a positive sign, of course. So the factors of 3, since 3 is a prime number, we know the factors are 3 and 1. So let's just check. If I multiply 3 and -1, I get -3. If I add 3 and -1, I get +2. So this works perfectly fine. Then I can get my roots or my x-intercepts. So that means -3 and 0, 1 and 0. Seems like I have everything that I need now to be able to sketch the function. Okay, the shape sorted, the axis of symmetry, which then led me to writing down the turning point, the x coordinate, the inverse of p, which is the x coordinate of the turning point, the q value as it is, which is the y coordinate of the turning point, the y-intercept I need to find. We let x be equal to 0. We substitute into that function. X is equal to 0, and this is what you have. 0 plus 1 in brackets, the whole thing squared, it gives you 1. 2 times 1, BODMAS. 2 times 1, multiplication before subtraction. 2 times 1 is 2 minus 8 is -6. This here is 0 and -6. Then we let y be equal to 0 in that same function, guys. Right? And just for convention, equal to 0 on the other side, so that we can solve for x. And please, yo guys, you know sometimes people butcher things here. X plus 1, the whole thing squared, they apply the square to the x, they apply the square to the 1, and they think they are on the money. No guys, please, let's not forget that this is a binomial, and then there's a bracket, there's a square, so that means we open 2 brackets, we FOIL. we should get x squared plus 2x plus 1 inside that bracket. We then distribute the 2 that's outside the bracket to just the bracket itself, and then after that we add and subtract like terms. Okay, so that's very important. Don Chavala, that's a nice question, but for now we are still doing the fundamentals and the foundational basics, so that will come along in further lessons. But for today we're not going to look at that. So thank you for your consideration, and I think for those who are here in the platform, if you are seeing this, a question that Don Chavala has put there in the comment section, it's a good question to actually consider. But for now, like I said, we're just looking at something so that we can emphasize that particular thing, and you can rest assured we will get to that and we will be able to explain it further so that there can be clarity. But for now, we are just here. So now that we have all the aspects, okay, then we can go ahead now and sketch the function, which is very important. We can sketch the function using the information that we have just gathered, all right, that we have just gathered. So let us go and now sketch the function. We have the x-intercepts. Our x-intercept were -3 and 1. So -3 and 1. Okay, then our turning point there, we have -1 and -1, okay, with the y coordinate being -8. Okay, so the way these two meet, that's where our turning point will be. Then our y-intercept is very important, so it is 0 and -6. So 0 and -6, -6. Okay, we can just have it here, very important. Then we can go ahead and sketch. There it is. We turn. Okay, and then we make sure we have that axis of symmetry of ours. So we know that x is equal to, that axis of symmetry is x is equal to -1. We just make sure now we write down our coordinates of the turning point. Our y-intercept is there. We can clearly see we've marked the -6. We have the 1 there marked very nicely. We have the -3 marked there very nicely. And then the shape of the function, so that we can ensure that we are spot on the money. Just a little bit of mercy, guys, there, okay, with my free hand with the pen. But of course, that is how we sketch the function. Then we label it, of course. Y is equal to, the form that it was in was 2x plus 1, the whole thing squared, minus 8. All right, and then that basically gives us a fresh sketch that we can be very confident about. So guys, the two forms, let us not forget them. The quadratic form, okay, please, very, very important. And then the turning point form. Okay, just generalize. Okay, so our grade 11s, we have entered into a new zone when it comes to quadratic functions, and these are the forms that we ought to know. Okay, yeah, and we've spoken about the A, the B, and the C for the quadratic form. We've looked at a sketch, we've looked at how it pans out, and then we've looked at the form, the turning point form. We've looked at A, P, and Q, and we've looked at what effect does each respective parameter have, okay, and how it affects things for us as we go along. So I hope that is very clear for all of you. So what I'm going to do now is I'm going to actually leave the A on the turning point form also speaks about the shape of the function, okay? Still speaks to the shape of the function. So the A here and the A there, they still mean the same thing, all right, for both, okay? And what's also nice is that even in term 1, when you were completing the square of this expression and you got this form, you will remember that you were able to determine whether you are reading the minimum or the maximum depending on the a value, because you know that when a is greater than 0, that means concave up, and obviously that speaks to minimum, and your minimum value was always your q value. The x value that gave you the minimum was the inverse of p. All right, so these things are just, we are tying things back to, to each other, so that what we learned earlier on last year can actually make sense for us now. All right, and obviously when a is less than 0, you are still speaking about concave down, and obviously that speaks to your maximum. Okay, this is your maximum value. So your maximum value would also be your q value, as it is. Your x value that gives you that maximum is the inverse of the p value. Let's not forget that. And this is so important. Okay. Yeah. So when we have that down, then sketching functions, guys, won't be a pain. Okay. Whatever form you get, you should be able to sketch the function hands down. Hands down. And when we are able to at least sketch the function, we are able to see a visual image of what we mean, from a quadratic stance. Because, at an algebra stance, you can see that is the form. So you can have a visual representation of that algebraic form by actually sketching this thing here on a Cartesian plane, and you can see, oh, this is basically it. All right, this is basically it. So if I was to ask someone here, let's just look at domain and range, since domain and range is something that we seem to be looking at quite a bit. Can you guys tell me what would be the domain of this function? Let's see if you guys were able to grasp that idea of domain. The domain of this function would be what? Okay, Don, I see you, Don. Yeah, I mean, Don, obviously, it seems like you have like some expertise that you tag along with. My learners, what would you guys say would be the domain? What's the domain of this function? Remember, I said domain speaks to your possible x values, where the function exists, where the function is available from left to right. Is the function existing everywhere, or is it existing is it limited in its existence from left to right, or does it exist everywhere? Because if you can say the function exists everywhere, then ava motiba, what you've commented is 100% spot on. Okay, if the function exists everywhere. Okay, so hopefully you guys can, I like the x er. Obviously when we write x is an element of r. Okay, if you think about this being the letter, I know that today's teenagers and today's young people always have short forms for everything. I'm just imagining you saying, I'm asking you, where does the function exist from left to right? And you're like, it exists everywhere. Do you see these letters? ER, no, not really E, this is an element. But then this would be a nice way of you remembering that the function exists everywhere. So if it exists everywhere, it means X is an element of R. Just thinking of short form where someone would say everywhere, right? Everywhere. So that's basically it, everywhere. You've got the E, you've got the R for everywhere. So X is an element of real numbers because the function exists everywhere from left to right. The arrows are there, which denotes that there are no restrictions. Okay, so that would be our domain. So thank you so much, Ava. I can see we have Ava. Okay, then our range. What would be the range? Okay, Max, I see you there. You say y greater than negative 8. Is it just greater than negative 8? Yes, because we are always looking at the y value, the y coordinate of the turning point. So that definitely features. Okay. The question is, does the function exist at negative 8? Since it's the lowest point, does the function pass through negative 8? If it does, then does it touch negative 8? If it does touch negative 8, then it means that the function also exists at negative 8. So how would we actually then represent that? Okay. So we say y is greater than or equal to negative 8. Let's not forget the equal sign. If there's no equal sign and you simply say y greater than negative 8, it is incorrect because it's incomplete. Okay. Yeah, remember, it's not just function existing above negative 8, it also exists at negative 8 and above negative 8. So then we say y is greater than or equal to negative 8. That is our range for the function. Okay. So I'm going to insist that whenever you sketch a function, you sketch it and you also write the domain and the range. If you can do that for me, that would be very nice. Okay. Something else to note as well, I could ask you this question. For which values of x is the function decreasing? For which values of x is the function decreasing? For which values of x is the function increasing? So first, let's start where the function is increasing. Decreasing. For which values of x does the function decrease? Okay. Values of x for which function decreases. So I'm sure you guys remember what I said earlier on when I was talking about the decrease of the function. What's happening here from left to right? Because we are moving from left to right. So when we're moving from left to right, we need to observe what's happening as we move from left to right. Okay. People generally love moving from a negative place in their lives to a positive place in their lives. Okay. Like for instance, a lot of people are hoping to go to heaven. Why? Because we imagine heaven being a place of paradise, a place where there's peace, where there's happiness, where there's no longer mourning, where there's no bad things that happen. So naturally, we are inclined to want to move from a place of negativity to a place of positivity. So, it also goes with marks. Some people, term 1 may have not performed as they would have wanted to. So what everybody wants right now is to make sure they have a fair fight, and basically in term 2, they can actually improve their marks. We are people that are constantly seeking to be better and improve and be better than yesterday. So what I'm saying is, as we move from left to right, what's happening? If the function is a smiley face like this, from left to right, what's happening here? It's decreasing. So we are decreasing here. We are decreasing here. Look at the x values. Where are we coming from? From negative infinity. We are decreasing. We are decreasing. We are decreasing. We are decreasing. And all of a sudden, our x value, when we get here, there's a change in the decrease. Now we are changing and we are actually doing what? We are increasing. Okay. So something's happening before this value of x. So we need to check what is this value of x where the decrease is happening. Okay, this side, it's when x is less than this value of x, which is -1. So when x is less than -1, the function is decreasing. Okay, very important. Values of x for which the function decreases, it's when x is less than -1. Okay, then you want to ask a different question. For which value of x, for which values of x is function increasing? For which value of x is the function increasing? Okay, so remember, where are we now? we are at x is equal to -1. Okay, we are at x is equal to -1. Now we start, look, we increase. But what are these x values where we are increasing? It's where x is greater than 1. Okay, that's where we are starting to do what? To increase. Okay, right, so there's an argument that's happening, you know, in the maths world, but you see, the thing is, that argument that we have in that maths world, all right, there's sort of like a standardized judgment that has been made within the context of the FET phase. Okay, and within the context of FET phase, we have basically said that if learners basically say x is greater than 1, we give them the marks. If learners were to say x is greater than or equal to 1, we would still give them the marks, because there's an argument about the accuracy of our answer, whether it be greater than or equal to 1. So some other learner might say to you, where is the function increasing? They would say, no, the function is increasing where x is greater than 1, but also where x is equal to 1. All right, so what we've basically decided in the maths community, all right, within the FET band, within the South African context, we've decided to basically allow learners to basically answer with greater than if they want, or greater than or equal. So in some cases, you'll have a learner say x is greater than or equal to 1. Okay, we accept that answer as well. All right, we do not penalize a learner if they decide to say x is greater than or equal to 1. Okay, we accept both answers. So because there is an argument, there is sort of like an argument for the answer being a certain way and not being another way. So all in all, what we've decided in the community, within the maths community, is to accept both answers just for the sake of that particular argument. All right, so we just leave it like that. So if you write x is greater than 1, just remember, I mean, we are just increasing, because you can see most what's happening here. There's an increase. As x increases, y is also doing what? Increasing. So that is an increase. This side, as x increases, y is decreasing. So there's a decrease here. We're going down. Here we're going up. All right. If it was vice versa, if it was a concave down function, I'm sure you can see, guys, as well what's happening here. From left to right, what's happening from in this side? There's an increase here. There's a decrease here. So increase here until that axis of symmetry, and then decrease there. Okay, so we are always using that axis of symmetry, that value of x for our axis of symmetry, to basically write our answer. So it's either we are, if I say for which values of x are we decreasing, just check first what is the x value, what is the x coordinate of the turning point. Then if we are concave up, then for which values of x is the function decreasing? It's when x is less than -1. For which values of x is the function increasing? It's when x is greater than -1. If we had this function, right, this side, and I asked for which values of x is the function increasing, obviously, guys, we are increasing, right? In this side, x is less than -1, we are increasing. Okay, that's if this was a -1. I'm just saying for argument's sake. Remember, guys, it will change for depending on whatever parabola you have. Okay, but this side we would be decreasing. Yes, that's fine. That's fine. So for increasing here, this side, if you said x is an element of -1 to infinity, that's fine. That's 100% fine. Okay, whether the learner says square brackets or whether the learner says open brackets, because remember, like I said, the argument of whether we include that value of x or we don't is something that is on. All right, and basically in the South African context of our syllabus, even at national level, when they mark the learners in your official final exam at the end of the year for grade 12, they will accept and embrace if your answer is like this, or if your answer is like that, or if your answer is like this, or if your answer is like that. Okay, so I hope that is, clarifying whatever ideas or thoughts that one may have had. So guys, I'm gonna have to stop right here. I think I'm gonna leave you guys with a challenge, and basically in this challenge what I'm gonna do is I'm gonna ask you to sketch a few functions, identify the domain. So let's do this. Let's say this is our game challenge. Okay, obviously this is not parabola covered and done and dusted, but I do want to go up to a certain point and allow you guys to then digest what we have covered today, rewatch it at your own time if you need to, and then what we can then do is I can continue on with the rest at another time. So our game challenge, sketch the following functions. That's one. Then two, I'll sketch the following functions, label x int, y int, turning point, axis of symmetry. I think all of those need to be there in the function. X-intercept, y-intercept, turning point, axis of symmetry. That's what you need to do first. Secondly, give the domain and range. 3, for which value of x is the function that you have sketched. A, for which value of x is the function increasing. Then B, for which value of x is the function decreasing. Okay. All right. So these are your functions that you're going to be sketching: A, B, C, D. So your first one, f of x is equal to 3x² two So you're gonna sketch each function individually, right? You're not gonna sketch not gonna sketch all these functions on the same set of axes. You're gonna sketch them individually. So you're gonna sketch you're gonna sketch, for instance, A and answer all the question. Sketch B, answer all the questions. Sketch C, answer, and so forth. I hope you guys get my drill here. Okay, I think that's, yeah, that suffices. Okay, so we're just getting into the swing of things, guys, into the groove of things. I hope these problems are fine and sufficient. Okay, I don't know if anyone has any particular question that they have right now. If you do, I'd be happy to entertain that. If not, then I guess that pretty much brings this session to a nice end. I hope it was really fruitful. Like I said, the first question says sketch the following functions, label your x-intercept, y-intercept, turning point, and axis of symmetry. And you are sketching each function individually. After you sketch each function individually, you give the domain and the range of each function. Then 3, you answer the question for which value of x is that particular function increasing, and then where is it decreasing. So you answer all these questions for each function. You sketch this function, you answer the question. You sketch this function on a separate axis, you answer the question. You sketch the function, you answer the question, and you sketch this function, you answer these questions. Okay, anyone with any particular question right now, besides of course questions that yeah, but it has to be related to what we've just covered. Any particular question or anything? What? Seems like there's nothing. Right, so those are grade 11 functions. I will be posting, I'll be downloading and posting this video on my YouTube channel. If you haven't followed or subscribed to the YouTube channel yet, please do so. I have a video that I posted up a few days ago on Euclidean geometry. I started circle geometry for grade 11, the theorem that says the line from the center to the midpoint of the chord is perpendicular to the chord. I did that theorem, and then we looked at some examples, rider examples, where we answered some questions using that theorem. And then the other one that says a line drawn from the center perpendicular to the chord bisects the chord. Also looked at examples. I really explained, tried to unpack the concept around that particular theorem and then its application as well. So yeah, please go to my YouTube channel. Link is in the bio. You can like, subscribe, follow, comment, do all sorts of things, man. Make yourself visible. Just do what you need to do, and please, I'm happy to answer any of your questions. So yeah, if you're really burning to ask a particular question, please do use the guest option as well. Yeah, and whatever you need, you must let me know. Thank you so much though for joining in. I hope your session was fruitful, that there was some things that you picked up and which will be valuable as you enter into the next term. So yeah, thank you so much. Please have a greatest of night, and maths is a game indeed, and hope we can continue to play it well. Cheers. You're welcome, Ava. Thank you so much for actually participating the most. Really appreciate that as well. And Luanle, thank you as well for the gifts. I really appreciate those too.